Hello, I'm Mary Page Bailey, Associate Editor at Chemical Engineering Magazine. Thank you for joining us for today's webcast, A Practical Guide to Sustained Heat Transfer Fluid Performance. We hope it will be informative and useful for all of you. High temperature processes depend on heat transfer fluids to ensure continued reliable operations. When a heat transfer fluid is not performing at its full potential, it can impact processes in many ways, including decreased production rates, wasted resources, and reduced product quality. A better understanding of heat transfer fluids and their performance can lead to more efficient operations. This webinar will provide guidance on many aspects of heat transfer fluid quality and troubleshooting, with the aim of improving process performance. Our speaker today is Conrad Gamble of Eastman Chemical Company. Conrad Gamble is a senior product steward with Eastman Chemical and has over 30 years of experience in the chemicals industry. In his current role, he supports Eastman's Thermonol business in product development and customer technical support, and also provides educational training. Conrad is a licensed professional engineer and a recognized industry expert. He holds a degree in chemical engineering from the University of Alabama. Listeners will have the opportunity to send questions to the speaker during the presentation, and these questions will be addressed during the designated question and answer period. On the left of your screen, there is an area where you can type and submit questions to the speaker. Feel free to send in questions at any time during the presentation. We will answer as many questions as possible. If you are experiencing any technical difficulty, you can type that problem into the same area at the left of your screen, and someone will assist you. This program will be archived for future viewing. You can use the following URL, www.chemengonline.com/webcast. With that, I'll turn the program over to the speaker. Conrad, please go ahead.
Well, thank you, Mary, and welcome to everyone attending this webinar live and afterwards who are accessing the recorded session. I do thank you for your time today. Based on the number of registrants, this topic is one that has importance to many of you, and it's true not only for the mere economics of extending the usable life of your heat transfer fluid and operability of the system components, but also it helps to avoid tying up your valuable engineering and people resources which are spent troubleshooting the problems in your plants. Those resources should be and can be better spent elsewhere in other areas. So hopefully this information we share today will be educational and informative. We should have plenty of time at the end, so I encourage you to submit your questions. First and foremost, the processes requiring heat transfer fluids will not run properly nor as efficiently when the fluid's in poor condition. This can result in reduced throughput, increased energy costs, increased risk of fouling and equipment damage, an increased frequency and unplanned downtime, and tying up resources that are spent searching for problems and solutions of the issues in process areas. All of these components add to the cost of manufacturing our products. These are costs that can be minimized when the fluid and the systems are kept running optimally. I know that when pushing a heat transfer fluid to work at very high temperatures, that stresses can and will induce degradation in its chemistry and in its performance over time. However, our goal in today's topic is to understand what those stresses are and what strategy can be implemented to best manage them to get the most out of our fluids for the longest possible time. There's a white paper that we've previously written on optimizing heat transfer fluid performance, which is available for download from our website, thermonol.com, at the web address shown here. Building upon that article, today I'll share information that will help sustain this performance and slow the impact of those factors that can age fluid and deteriorate its performance. Let's review the threats to the fluid first. Changes in fluid quality can include changes in its composition and its physical properties. As the fluid thermally degrades, the percentage of the original components decreases as the concentration of degradation products that are forming increases. Routinely, the fluid in an organic heat transfer fluid system will require makeup fluid addition periodically to offset losses from the system from leaks, spills, maintenance, and venting. Normally, in a well-designed and maintained system, this makeup usage can amount to near 3% per year on average. The addition of fresh makeup fluid can partially restore the fluid chemistry toward new condition, but only in a small increment. When the fluid degradation rate outpaces the makeup fluid addition benefits, a growing deviation from new fluid condition is experienced. And this results in a change in the fluid's physical properties. The key physical properties of interest include liquid density, heat capacity, thermal conductivity, and viscosity, and some other important attributes of insoluble solids content and acidity. Analysis of representative samples of organic heat transfer fluid chemistries have found that over the typical life of a fluid, the liquid density, thermal conductivity, and heat capacity do not vary significantly, perhaps a 2 or 3% deviation from as new. Viscosity, though, can vary significantly as the fluid ages. Since these four properties are used in the calculation of the fluid side heat transfer coefficient, the viscosity then is prominently highlighted as very important due to its potential for greater change. The acidity, or total acid number, sometimes called TAN, can vary dramatically if not protected from contact with the oxygen in air. This can lead to corrosion and other equipment reliability impacts. Oxidized fluid commonly exhibits increasing concentrations of insoluble solids, particularly with increasing temperatures, as the organic acids which form are more vulnerable to thermal stresses and can have limits to solubility in the fluid that result in their precipitation as solids or sludge. Operation with elevated solids content can lead to fouling of heat exchanger surfaces, which will impede heat transfer rates. At lower temperatures, the acids can accumulate to greater concentrations and increase the fluid viscosity. Fire properties like flash point and fire point can be measured and are generally linked to the low boiling degradation product concentration. Lower boiling low boilers can have the greatest impact on flash point reduction. By examination of the chromatogram developed during the fluid analysis, one can be guided on the need for measuring flash point. When there's an insufficient presence of low boilers in the fluid, it can make the flash point test itself inconsequential. A second threat to the fluid is changing ability to meet the process requirements. But beyond the fluid's capability itself, the process may also evolve to new operating conditions with new circuits or system changes that may impact fluid flow rates through the equipment. Any proposed changes to the equipment should be reviewed to identify the potential need for increased fluid volumes and flow rates that might be necessary to meet these new demands. As mentioned, when the fluid viscosity deviates to greater values, this reduces the heat transfer fluid side heat transfer coefficient, H, and reduces the overall heat transfer coefficient, U, as a result. This can have a greater impact to processes which are heat transfer fluid side limited, such as aqueous processes, and have less impact to those that are process limited, such as heavier organic streams. If the fluid quality supports fouling, then the heat transfer efficiency will suffer. Responses to these changes can be varied, but can create further stresses to the fluid. For example, an immediate response is to increase the outlet temperature from the heater so that the fluid is hotter, creating a higher delta T to get the energy into the process. That can work for the short term, but it also results in an increased rate of thermal degradation to the fluid. Compositional changes are primarily induced from thermal and oxidative stresses. Oxidation of fluid requires high temperatures, generally above 80 degrees Celsius, and contact with oxygen. Commonly, this occurs in the expansion tank of a system. In non-inerted tanks, it's important to keep the fluid temperature cool in the tank and to avoid enhanced exposure to air. And by that I mean limit the amount of temperature cycling that allows the air in the tank to be refreshed as the fluid expands and contracts in volume. And avoid air entrainment in the fluid that can be caused by agitation at the liquid surface within the expansion tank, or splashing of a return stream into the vessel, or allowing air to mix with the fluid before it's circulated through the heater, such as a vortex being formed in the bottom of that vessel when the liquid level is low. Inerting the vessel with an inert gas will properly and fully eliminate the oxidation mechanism from occurring. Now, thermal stresses are applied in the fluid's heat source, whether it's a fired heater, a waste heat recovery unit, or another heat exchanger in the process that provides heat into the heat transfer fluid. Be sure to keep the fluid within its published allowable bulk and film temperature limitations to get the full life out of your fluid. Your fluid supplier should be able to analyze the fluid to quantify the degradation products and acidity, and then make appropriate recommendations as needed to adjust that quality. A key point to stress is the best use of a sample analysis program is to detect early trends that lead to taking action before the fluid is significantly damaged. And this means being diligent about taking routine fluid samples for analysis before there's any perception of a problem in the fluid. Compositional changes can occur from mixing of fluids, either by necessity or accidental, by venting and overventing, and replacement while leaving a heel in the system. And I mean a heel, what I mean by a heel is residual fluid that you just can't seem to quite drain and get out of the system. Compositional changes, of course, are changed by fluid addition as well. Compositional changes would naturally lead to changes in performance and fluid life, depending upon what and the degree of the change that occurred. Contamination events are the most troublesome, since the contaminant is very likely of lower thermal stability than the heat transfer fluid itself, and that leads to its rapid degradation and potential impact to other equipment-related consequences. Oxidation can lead to several costly consequences, including viscosity increase in insoluble solids content, and fouling, all of which cause decreases in the fluid side heat transfer coefficients. It also increases the acidity that's corrosive to carbon steel surfaces, particularly in the vapor space of the expansion tank. There are numerous instances of corrosion which has led to the required repair or replacement of nozzles on the top of expansion tanks, or replacement of the entire expansion tank itself, as well as leading to leaks into insulation that accompany greater fire potential. Thermal stresses to the fluid are time and temperature dependent and can change the physical properties of the fluid primarily by a gradual shift toward higher average molecular weight of the fluid over time. This is occurring as the lights or low boilers are vented from the system, and the high boiling degradation products with higher molecular weights are accumulating. Contamination with processed fluids or other heat transfer fluids can create an immediate change in properties that are proportional to the mix ratios. This can impact vapor pressure and boiling point, flash and fire point, and viscosity, and can potentially lead to pump cavitation or premature system venting. Most heat transfer fluids are relatively non-reactive, but contaminants may degrade within the heater coils to form coke deposits and create operational safety concerns. If a contamination event does occur, it would be best to contact the heat transfer fluid manufacturer to discuss the incident and which fluids were involved, to together work toward the potential consequence or understand the potential consequences and possible actions to take. I include color and odor here on this slide, not because they are key indicators, but to address their only minor ones. Color of new fluid is typically very good, ranging from water white to amber, and almost always transparent and free of significant particles. As the fluid ages with thermal stressing, the fluid will typically darken as high boiling degradation products are formed. Only a small amount of high boiling compounds is necessary to impart a color to the fluid. The attribute of color itself has no bearing on the performance of the fluid for heat transfer. High moisture content is included here, as it sometimes can create an emulsion and a discoloration of the heat transfer fluid. High moisture content can lead to pump cavitation and increased system pressures, but it has nothing to do with the color or the appearance of the fluid, but rather with the increased vapor pressure the moisture provides. Very high moisture content can prevent stable operations at high temperatures due to boiling of the water, trying to go into vapor phase. Similarly, odor can change as the lower boiling impurities accumulate in the fluid. Odor and color should only be used as secondary indicators of fluid quality change, but they really do not directly impact the fluid performance. A properly matched fluid to the process will provide long service life. This proper matching means that routine and expected operating conditions and temperature control will not cause undue fluid damage. For example, a fluid rated to a maximum bulk temperature of 600 Fahrenheit that's also operated at this maximum temperature may experience damage if there are upsets, such as heater outlet temperature control overshoot, power blips, or stopping the fluid circulation before the heater is adequately cooled. Consider, if this is in your plant, consider how to reduce frequency of power interruptions and controls overshoot incidents to minimize the periods of excessive thermal stresses these incidents can apply to the fluid. Also, review and modify operating procedures as needed to ensure that the residual heat from the heater is adequately dissipated before stopping the circulation pumps for shutdown periods. Alternatively, you could choose a fluid that's rated to a maximum temperature well above the expected operating temperatures. In that way, the fluid is much more capable with built-in capacity for those temperature overshoots. The system design should also have the capability provided to support fluid quality maintenance. The maintenance involves fluid sampling capability, occasional removing of excess moisture and excess low boilers, removal of solids, addition of makeup fluids, and protection against oxidation of the fluid. Insoluble solids are best removed with a side stream filter, where we suggest 1 to 2% of the circulating flow is diverted through the filter. This allows several system volumes to pass through the filter each week. An illustration of a sample collection port is at the right. The goal here is to allow safe collection of a representative fluid sample for analysis. This particular design allows for flushing of the sample chamber and collection into a sample bottle after the isolated sample volume has cooled. The next slide shows a graphic that illustrates the features needed to manage the remaining concerns. So in this slide, we show an illustration of the expansion tank and the associated piping. Along the bottom of this slide, from right to left, you have the return header that's flowing liquid from the process back towards the circulation pump, and from the pump it goes on to the heater. We see two drop legs of piping that connect the return header to the expansion tank. Along the return header, you see valve A, which is normally open, and on the drop legs of pipe you see valves B and C, one of which needs to be open at all times. Another important valve on this slide that I'll talk about is valve E, which is at the upper right on the vent line. So now let's get into what this slide illustrates. It shows the expansion tank design features needed for fluid quality maintenance, specifically for the venting process. The key is to have a capability to flow through the expansion tank. Excess moisture and low boilers can be vented from the system by recirculating through this tank and then venting to a safe location. At the upper left is shown an inert gas that's added to the expansion tank with its supply regulator. An outlet line at the upper right with the back pressure regulator set slightly greater in pressure maintains a static blanket of pressure on the vessel while it's not venting. A continual purge is not needed and would actually harm the fluid by promoting excessive venting and stripping out some of the lower boiling components that you'd really need to keep in the fluid mix. The selection of the inert gas should ensure low oxygen content, typically less than 1%, and usually is selected to be nitrogen. The pressure applied to this vessel should be no more than necessary to ensure the NPSH requirement of the pump is met, and that includes the liquid elevation head provided to the pump. So the venting process is supported by closing valve A and opening both valves B and C to get circulation through the tank. The tank contents warm and the vapor pressure of the lower boiling components increases with that increased temperature. You open valve E on the vent line, and then the pressure and flow of the inert gas sweeps out the low boiling products, gases, and moisture out of the system. This is shown to condense and be collected for the proper disposal. Whatever you vent out is called vent condensate in this vessel, and it is not to be returned to the system. The purpose is to remove them and then provide for proper disposal. Larger systems can typically vent directly to a flare. When you finish venting, close the vent valve and then return the valves A, B, and C back to their normal positions that bypass the expansion tank. Bypassing the expansion tank allows the fluid within the tank to reach cooler temperatures, reducing the thermal stress on that portion of the system's fluid. And that portion is typically 20 to 25% of the volume. This design also allows for fresh fluid makeup into the expansion tank. Addition there would have least impact to temperature variations with some sensitive processes and less problems with flashing of moisture if the makeup fluid has high moisture content. Bulk storage tanks should have a slight positive pressure to avoid humid air entering and condensing the moisture onto the vessel walls, particularly in humid environments. Care in the storage of makeup drums should ensure that water or snow doesn't collect in the drum lids if stored outdoors. Either store them on their sides or with rain caps or store them indoors to protect against the moisture ingress. Also, ensure they remain well labeled as new fluid, and this prevents people from accidentally pouring other fluids, say used oils, into these drums. When replacing aged fluids, attempt to remove as much of the old fluid from the system as possible before refilling with new. The old fluid residues, or heel, left in the system can actually promote faster thermal degradation rates of the new fluid. Consult with your fluid manufacturer to help design the fluid replacement process to safely remove and handle the old fluid that includes its proper disposition for disposal or recycle. We've seen that oxidation in fluid aging can increase the fluid viscosity. The chart at the right shows a relative change in fluid side heat transfer coefficient, H, resulting from an increase in the viscosity at operating temperature. This change over time can consume the excess surface area that's provided in your heat exchanger designs and can ultimately lead to production rate impacts. Protection against these costly impacts can be provided by the effective use of the inert gas blanketing and by ensuring the fluid is protected against the high temperature excursions and excessive venting. Excellent information related to good system design can also be gleaned from insurance providers and from the NFPA 87 standard for fluid heaters. To minimize risk of contamination, ensure shell and tube heat exchangers utilize strength welded tube to tube sheet connections. These connections, when rolled, are perhaps the greatest source of process end leakage and are made worse with increased frequency of temperature cycles. Ensure that the reuse of drained fluids and vent condensate is not permitted, as these fluids are many times oxidized and can also contain other contaminants. Use only the proper makeup fluid for the system by establishing good labeling of system fill ports and makeup fluid drums, along with adequate personnel training. Conditions in the plant can sometimes be less than ideal, and erroneous fluid addition has occurred. Most fluid manufacturers will offer fluid analysis support. Be sure to make a connection with your manufacturer to establish that relationship and secure that support that they provide for you. Routine sampling is necessary to establish the data that's needed for trend analysis prior to the onset of your problems. Fluid monitoring is not only the task of the lab. Process engineers can utilize key indicators of the process to monitor for fluid performance change. Identify and trend key indicators in the process, which can include heater outlet temperature, the temperatures in and out of process heat exchangers, both on the heat transfer fluid and on process sides of the exchanger. Examine energy balances around the heater and process users, and pressure drop through circuits. Several process monitoring points are shown on the right side of this slide, which can provide indicators of fluid performance. Then use the fluid analysis services provided by the fluid manufacturers, who know their fluids the best, to provide the educated interpretation of the results and guidance on actions to take. A recommended heat transfer fluid monitoring plan should assess and trend the key indicators shown here. Early detection of trends is key to effectively protecting and sustaining the fluid's performance. The fluid manufacturer should be the best capable of comparing the results obtained to those expected for the specific chemistry of fluid and the time in service at the given temperature. Third-party labs can provide results, but they can be lacking in their interpretation for a specific fluid chemistry. Once a result indicates a potential problem, then investigation and possible actions should be considered and taken. I wanted to give a few examples of sample analysis and when action was taken or ignored. First is an example of no action taken. One customer at one time failed to monitor their fluid at all with routine samples for a number of years. And finally, they submitted a sample for analysis, and the results showed that the fluid viscosity at 100 Fahrenheit had reached over 700 centistokes. This is several times, many times, above the action limit for this in-service fluid. They were unable to shut down the unit due to production demands, and so they implemented a plan for successive partial dilutions or on-the-fly dilutions while running over the next 12 months to restore the viscosity to an acceptable value until it could be shut down and fully replaced. In the end, this was successfully accomplished, but it incurred greater potential for safety incidents by running with that high viscosity, and it also incurred much greater fluid costs over time. Another customer submitted a fluid sample that was measured to have a viscosity that was very much unusually high for the age of the fluid and the service temperature that they were operating. The fluid specialist identified from the lack of low boiling degradation products that were present and the reduced amplitude of the lower boiling fraction in the gas chromatogram of the heat transfer fluid that the fluid was experiencing excessive venting or overventing. After consulting with the customer, there was found a continuous stream of nitrogen that was blowing through a portion of the system and into and through the expansion tank that was continually sweeping vapors out to their flare. Correction of that issue allowed an adjustment of the fluid quality by working together from the customer with the fluid manufacturer that restored its composition, and it extended its usable fluid life while also correcting for the costly nitrogen usage issue. Another example is where a customer found from the sample analysis that their low boiler content had reached 7% after about 3 years. Now that's above the 5% recommended maximum low boiler content that's recommended. Their expansion tank design did not permit circulating the flow through the tank as in the design drawing that we looked at a few slides ago. And so efficient venting for low boiler removal was not possible. In the end, they performed a 50% fluid replacement, which diluted the low boilers from the original 7% down to 3.5%. But for future operational performance and fluid maintenance, they implemented a design modification that would allow circulating flow through the expansion tank. This permitted them to achieve low boiler removal just by maintenance of venting from the system, as we described earlier. That reduced annual makeup rates to near 3%. The relationship established between the customer and the fluid supplier helped match their system design needs to support the fluid maintenance requirements more cost effectively. I have one more example of fluid trending analysis. We had a customer once who was operating at a high temperature above 600 Fahrenheit for a number of years and had very good service life and performance. They practiced regular sampling and analysis with the fluid manufacturer from the system startup, and so they had a wealth of data available. In later years, the fluid degradation rate was observed to have increased faster than their earlier projections. By analyzing the historical trend of fluid degradation products and the viscosity changes, a window of time was identified to be associated with the onset of the fluid degradation rate change. Consultation with knowledgeable engineers at the site determined that during that time there was an addition of a new burner made to the heater so that a waste stream could be utilized for its energy value. This change to the heater created added thermal stress to the fluid in the coils and was responsible for the increased degradation rate. The customer then had the facts necessary to make the adjustments to their operations to better protect the heat transfer fluid and extend its life. This also highlights the importance of thoroughly reviewing any design changes to the heat input sources for their potential impacts to the fluid. The heat input sources are the first place to look when investigating possible causes of excessive thermal degradation of the fluid. While fluid quality monitoring can be accomplished with annual samples being analyzed, there's no need to ignore the 364 days in between. Here is shown an example of components of a system monitoring strategy that can be compiled for a specific site and system to help track performance over time and to ensure the systems are running properly to avoid impacts to the fluid and equipment. These lists are not comprehensive and could vary among equipment of different designs. Looking at the inert gas supply section in the center, we see at least 8 attributes can be periodically checked to ensure the system is still running properly. Perhaps tags could be placed on the valves and pressure regulators to readily indicate their normal positions of open and closed or properly set pressures. Application of such a list of checks for heat sources, filters, pumps, heat exchangers, safety alarms and interlocks, fire protection systems, and more can be uniquely developed and tracked to ensure your plant's system integrity and operation is at its best. I'd like to now issue a challenge to all of those attending the webinar today to establish a site goal and system monitoring strategy for your heat transfer fluid system, which could incorporate these concepts into your own site strategy. Develop the monitoring list for your system's equipment and utilize the technical resources from your own fluid, heater, pump, and filter manufacturers for a comprehensive list. Then establish a baseline check for the first month and document what is found. The first draft may require refinement, but that's okay. Train your personnel to take ownership of the monitoring plan and encourage reporting of any deviations for area owners and operators to follow up as appropriate. After a year of doing this, look back to evaluate the process in terms of the effort required and the payoff that was achieved. It's hard to quantify a cost avoidance, but each year the system and the fluid sustain their performance at the best is a goal accomplished. So I thank you for your attention these past 35 minutes or so, and I'll be glad to take any questions you might have. Mary?
Thank you, Conrad. That was very informative. We've had a number of questions come in. We have a question from an audience member that asks if you can provide any guidelines for a situation where they might be unable to detect heat transfer losses in their system.
Well, it sounds, in that instance, you need to have the addition of some process indicators that can give you that visibility. In a good system design, you need to have key process indicators that can let you know when your process is running well and when it's deviating from that. So without those key indicators, I'd say the first thing you might need to do is sit down and evaluate what data would I like to have that I currently don't have, and make that list, and then review that with some other key owners of the process, and then make that change. Propose the change to add those indicators. That could be things like flow meters, pressure indicators, temperature indicators, and so on.
Okay, great. Thank you. We have another question that asks, how long should the venting process take in terms of system cycles?
Well, I'm sorry, Mary, would you repeat that question, please?
Oh, sure. How long should the venting process take in terms of system cycles?
Well, that's a good question. The venting process can vary depending upon the design provision. We showed the two drop legs from the expansion tank connecting to the return header, and we suggest that the diameters of those drop legs closely approach the diameter of the return header itself. That way, when you align the valves to flow through the vessel, you have full circulating flow that's going through that vessel. That will allow a good turnover of the fluid in the vessel during the venting process and will improve the efficiency. Full flow will also raise the temperature in the expansion tank more rapidly, supporting the more rapid venting as well. If you were to have smaller diameter lines supporting the flow through the expansion tank, that's going to take longer. The best guidance I can give you is for a specific system is knowing the composition of the fluid beforehand, before you vent. Establish what you deem to be the standard venting process. Establish a venting time, say 30 minutes.
I think our speaker may have dropped off the line for a second. We'll give him a minute to call back in while we go through some more of these questions. Just bear with us here.
Okay, this is Conrad. I hope everyone can hear me again.
Yes, yeah, you're back online. Thank you.
Very good. I'm sorry, I lost the phone connection, so I'm calling in on the cell.
Oh, great. Thank you.
To finish my thought there, for a given system is to establish what you deem to be the standard flow rate and duration, and knowing the initial low boiling content based on fluid analysis, perform your procedure for your designated time, either 30 minutes or 1 hour. After that time, collect another representative sample for analysis. And that way, you know that for that duration of venting, you will have a reduction in X% of low boilers based on the fluid analysis. That's the best way I know to determine what you would need to do for a specific system.
Okay, great. Thank you. That's very informative. Our next question asks, what kind of filters are best and how to best install and maintain these filters?
Okay, that's a common question, and most people who use filters will find good success using glass fiber wound candlestick elements. They've also used metal mesh filter elements and bag filters, and they've been successfully used and demonstrated for many years. If you use the candlestick elements and bag filters, be sure to keep spare elements on hand for when you need to replace those. The metal mesh elements or backwashable type metal filters can be reused. On your filter housing, I recommend that the inlet and outlet flanged nozzles should conform to the piping specifications for the rest of your heat transfer fluid system. And be sure not to use threaded pipe fittings. These high temperature organic fluids have low viscosities and low surface tensions at those elevated operating temperatures. And so leaks through threaded fittings can be very difficult to stop. At very high temperatures, if you have leaks into the insulation around those threaded fittings, you do have increased fire risk. You want to make sure also the installation of your filter has pressure drop indication provided to know when the elements are dirty and the filter needs servicing. Lastly, I'd say you want to make sure that you have the ability to provide for total isolation of that filter when you need to change or clean the filter while the rest of the system is online. People will be servicing this. You've got very high temperatures there, so you want to make sure absolutely to have positive isolation. And I suggest a double block and bleed valve arrangement on the inlet and the outlet of the filter housing. I guess additionally, make sure that you have your filter that's got a good ability to be depressurized and fully drained prior to it being opened.
Thank you. That's very interesting. And of course, the safety and isolation is top priority. We had another question that asks if you can provide any recommendation of cleaners and how to best use them.
Okay. It can depend upon the purpose. If you are doing hot work on a system and you want to fully remove organic residues, to be very conservative about minimizing the potential for fire risk, I would say a detergent cleaner would be a good approach to remove the organic residues. That would need to be isolated as best as possible just to the section of piping or equipment where it's necessary. Depending on the fluid, you might it could vary which detergent cleaner would be recommended. Also, an old practice of using an acid wash base neutralization step and then a water rinse could be used to remove residues. It's very effective, but you have quite a bit of volume of cleaning fluids that are generated when you use that. But that's an effective approach when you're also needing to make sure the organic residues are fully removed, possibly for dismantling equipment and disposal. But if you have a need to clean a system of fouling deposits, what I would suggest there is draining the system and using the fluid from the system, and then using a cleaner such as Thermonol FF flush fluid. It's an organic cleaner, has excellent solubility of the high molecular weight organic deposits that can be in a system. So it can dissolve those. Any solids that are adhering to those deposits on the surface are lifted off the heat exchange surfaces, and with a circulating flow, they're entrained in are carried along with the fluid itself. So there's a process used for using this Thermonol flush fluid. It's been demonstrated and used for over 25 years. And it's an excellent cleaner to remove the common deposits you would see from organic heat transfer fluids. The value there is once you're through cleaning and flushing the system, you then drain all of that out and you're ready to refill with new heat transfer fluid at that point and start up your system. So you have much less volumes of fluid to dispose of as compared to the acid-based water rinse process itself. So you do have options. I'd suggest getting in touch with the fluid manufacturer to let them know what your needs are and and through that discussion, decide what is best.
Thank you. Okay, we have another question that asks if the heat transfer fluids can be regenerated continuously online.
That's an interesting question, and it can vary. The degree of regeneration can vary with the fluid chemistry. So, for example, Thermonol VP1 is a mixture of biphenyl and diphenyl oxide, so two components that have boiling points that are very close to one another. So the degradation products will be fairly lower boiling or higher boiling relative to those components. And if you do have an online regenerator that can effectively remove those degradation products and then supported by the necessary top-up of makeup fluid added back into the system to keep your system level fine, then theoretically you can regenerate that fluid for an extremely long time, maybe not indefinitely, but extremely long time. But however, there are other fluids which have wider boiling ranges. Most of your liquid phase fluids will have wider boiling ranges, and while you will have degradation products that occur in the lower boiling and higher boiling region, you will also have accumulations of degradation products within the normal boiling range of that heat transfer fluid itself. So the regeneration units would be able to take out low boilers and high boilers, but they could not treat properly the removal of degradation products that accumulate within the normal boiling range. So while you strip out low boiling and high boiling degradation products, you don't have light new fluid again. You have light new fluid plus a lot of degradation products that have not yet been removed. So it does. I do have to qualify that response in that way.
Okay, thank you. We had another question that asks, what is your opinion of mixing mineral oil with synthetic fluid?
Okay, that has been done before. So with most of the mineral oil synthetic combinations that you would likely see, there should be no chemical incompatibility between the two. However, if you have a mineral oil system, the components, O-rings, seals, gaskets, should be compatible with that mineral oil. Whenever you consider adding a fluid of a different chemistry into that mix, you need to also verify the chemical compatibility of those other components of the system with the new fluid that's to be added. There are some incompatibilities of natural rubber O-rings with synthetics where they are compatible chemically, or more so, with mineral oils. So you do need to be able to watch that. Now, another point is, what if you mix two fluids that have different degrees of thermal stability? Say one is rated for use to 500 Fahrenheit, the other to 600 Fahrenheit. Whenever you have a mixture like that, we do suggest that you derate the fluid mixture to the maximum temperature limit of the least thermally stable component of that blend. So a mixture of those two should be operated no higher than 500 Fahrenheit. The reason there is that the fluid of lower thermal stability will continue to have its own inherent degradation rate, and it is not going to be boosted by being blended with a fluid of higher stability.
Okay, thank you, Conrad. We have a question going back to the discussion we had earlier about filters. Can you provide some recommendations about the best filter pore sizes to use with these heat transfer fluids? Yes,
for normal operation, ongoing maintenance of a fluid quality, we recommend 10 to 20 microns. I have some customers of Thermonol VP1, which is a lower viscosity fluid. They will go down to 5 microns and maybe perhaps a little bit lower. If you already have a fluid that the report comes back where it's heavily laden with solids, you don't want to initially put in a 10 micron filter element in there. You'll want to start with more coarse fineness of the filter element, say 150 microns or so, and based on the frequency of replacement and of the elements and servicing of that filter, as the replacement frequency is extended, you can then go down to 100 microns, 75, 50, 20, and ultimately go down to 10. And that way you won't immediately blind over the filter that has too fine of a rating initially. So that's the way you would clean up a heavily laden system and fluid from the start, but generally 10 to 20 microns.
Okay, thank you. Now we have a question that asks, are there any actions or precautions that you recommend taking associated with heat transfer fluids during major plant turnarounds?
If you have fluid that's in a good condition and you need to de-inventory the fluid from your system to perform modifications to the equipment, for example, make sure the fluid is drained into clean, dry equipment, storage vessels or drums, and protect those from any ingress of moisture from the atmosphere or other sources. And if you properly protect that fluid in that way, when you get ready to put that fluid back in the system, it should be still in the same condition that it was when you first drained it. Depending on the fluid analysis at the time the system is shut down, there may be different things to consider, and that should be done or decided in consultation with the fluid manufacturer's representative, whether you need to do a partial dilution or what. So it's basically a case-by-case basis. So generally, the answer would be no, don't do anything unless you have to, would be my response.
Okay, thank you. We have another question asking, is a magnetic pump mandatory for pumping Thermanol heat transfer fluids?
No, by no means is a mag pump mandatory. We have a lot of people who are operating with standard horizontal centrifugal pumps with single or double mechanical seals. You have can pumps. You also have mag pumps. Some have positive displacement pumps. So it is one good option, though, but certainly not a mandatory requirement.
Okay, thanks. That's good to clear up. We have another question that asks, what is the best way to collect samples?
Well, that's a good question. I would strongly advise that samples be collected from the same sample port every time. That way you eliminate any variability that could be introduced into the analysis results if you were to catch them from different locations throughout your process. Also, make sure you provide adequate volume. We provide generally about a 1/2 liter bottle, and we would like to have that at least 2/3 full in order to have sufficient volume to conduct all of our tests properly. And if we happen to want to rerun a test or two, we have a little extra on hand. But provide a sufficient volume of the sample. Also, it needs to be representative of what's in the system, so it needs to be well mixed. So if you come off the discharge of the circulating pump, that provides a uniformly mixed sample so that the results are more meaningful when you get those back. From a safety perspective, samples should be collected cooled. For burn protection, I think typically below 140 Fahrenheit would help preventing thermal burns. From a sample integrity perspective, we do suggest cooling the samples to below 200 Fahrenheit and then promptly capping them in the bottle before moisture or low boilers have a chance of evaporating. If you're not using a bottle provided by the supplier of the fluid, it should be clean and dry. Always select a clean and dry sample bottle. The last thing I'd say is, there have been a number of occasions where we would have a sample and would report results with a parameter that was unexpectedly high or outside of our guidelines, and the customer says, oh, well, let me collect another sample and I'll be sure to collect it properly this time so we can trust the results. And so that ends up subjecting the chemical operator to 2 times of having to collect a hot sample instead of just one. So I would encourage people to always practice with each sample good practices to make sure each sample has good integrity.
Okay, thank you. We have another question that asks, how much makeup fluid should be added and at what frequency? And do you remove the fluid too with partial replacement or just add the new fluid into the system?
Okay, so makeup fluid needs to be added in order to maintain a desired liquid level. So for each system, you need to have a lowest allowable level indicated based on the level indication of the expansion tank. And then you would have a maximum level. So whenever you reach the lowest level, if you haven't already added makeup fluid, you need to add, that triggers the action to add makeup fluid, but not to add it above the highest desired liquid level in the system. So the frequency shouldn't be on a timetable, neither should the venting frequency be on a timetable. It should only be prompted by measurement of liquid level for when to add the fluid, and then based on fluid analysis results when needing to vent. I'm sorry, what was the other part of that? Oh, do you need to replace a portion of the fluid?
Yes.
Normally, if the fluid's in average in-service condition and quality, you would not need to replace a portion or drain some fluid out before adding the new fluid in. However, if you do have the luxury when running your system, if you have a very bad condition fluid, drain a portion out and then add new fluid in. So replacement of the bad fluid will have a greater impact on improving fluid quality.
Okay, thank you, Conrad. We have time for one more question. And then remember that our speaker will have access to all of the questions after the webinar. So if your question was not answered on air, you may have somebody follow up with you offline once the webinar is over. Our last question kind of ties into the last question. After what period should we replace our heat transfer fluids?
Okay, that should be based on the analysis of the fluid. Typically, if you keep a fluid within the guidelines provided by the fluid manufacturer for fluid that's in use, you should be able to continue to use that as long as it's maintained within those guidelines. So, and once again, you don't change the fluid based on a time interval. You change that fluid based on its condition. And the condition will vary, or the stress on that fluid will vary. Many processes run 24/7 every day of the year, so that can add more stress to a fluid that only runs day shift Monday through Friday, for example. So always base any actions taken to modify fluid condition based on the analysis results. If you have any concerns, please discuss that with your fluid manufacturer rep to make sure that they are in agreement and support the actions that are taken.
Excellent, thank you. It really goes to show how important understanding the condition of your heat transfer fluids and properly maintaining them is to all aspects of operations. So thank you so much, Conrad, for this informative webinar and for answering our many excellent questions we had come in from the audience. We're approaching the end of our time for this webcast, and to remind everyone once again, the program will be archived at www.chemengeonline.com/webcast. Thank you to the speakers, and thank you all for attending. We hope you will benefit from today's presentation. Have a great day.